Timekeeping is important, and its significance rises over and over with how advanced our technologies are. A precise counting of time enables mankind to have a GPS, internet, and space traveling. These things wouldn't be possible if not because of an atomic clock. Humans use clock from the beginning of time. Actually, many living beings use a day cycle as a clock. We humans observe the day cycle and start to call it a day. But its scales is as big as one day. So we invent clocks with more scales on it. Many types of clocks were invented. A sundial, a pendulum clock, a quartz clock for example. All of them have the same principle, to measure time with oscillation. We can use any oscillation to measure time as long as we know its period of frequency. For example, pendulum clock period is 2 seconds and the quartz oscillation frequency is 32,768 Hz. More frequency, more ticking sound, more scale, more accurate tiny bit amount of time we can measure. The same idea applies to atomic clock. In 1967, a second was defined using cesium-133 because cesium atoms are identical, so we won't have manufacture error like when we mix quartz crystals, and most importantly, it oscillates very fast. Here, we have the ground state of cesium-133, but it is split into two energy states. They are called hyperfine splitting. What caused this is relativistic effects and spin-orbit interaction. In short, this is hydrogen hyperfine splitting. If you have an unpaired electron orbiting around unpaired proton, it creates several ground states. But where does this number arise from? A cesium-133 atom is irradiated with electromagnetic radiation that has energy corresponding to the energetic difference between the two sublevels of hyperfine interaction. After that, it relaxes to the lower hyperfine level and emits an EM wave with some frequency. This frequency of cesium-133 is measured in terms of the second of ephemeris time. Ephemeris time is the previous time standard relating to astronomical observations, the Earth, the Sun, the Moon, and so on. The relative time of the previous standard and the new cesium standards are measured many times with averaging time of 2.75 years. And finally, scientists came up with a new definition of second, defined as a duration of 9,192,631,770 plus minus 20 periods of cesium-133 radiation when transitioned between two hyperfine levels. This frequency is corresponding to microwave frequency. After we know the frequency, it's time to construct a clock. There are many types of atomic clock built in a similar fashion, but in these videos I will talk about a fountain atomic clock. Scientists have built NISF-2, which is a cesium fountain atomic clock that provides current time standard. Inside it, lasers trap cesium atoms into a spherical sample, about 10 million atoms, and cool it to a millionth degree just above an absolute zero. From this to this, the sample is made sure to have only lower hyperfine state. Then it goes through the core cavity. At this cavity, the sample is irradiated by microwave to transition it from F equal to 3 to F equal to 4 hyperfine state. It continues to ascend along the supercooled tube and comes back to this position in about 1 second. At this same position, the sample is subjected to the same microwave. The idea of injecting this exciting wave twice after about a short period of time is referred to Ramsey interferometry, which I will mention later why. At the detection region, the excited atom is determined optically. By applying a laser beam, the excited atoms absorb and re-emit the light that is detected by the detector. If the clock frequency matches the atomic resonance frequency perfectly, the phase will be maximum. The microwave that gives resonance frequency is counted by microwave counter and calibrated to the number 9,192,631,770 Hz. The Ramsey method helps here. It makes the microwave counter to count the frequency much more precise. By doing this repeatedly, we get a consistently calibrated 1 second. NIST F2 clock calibrates other clocks around the world to provide the most synchronized time in every devices. This is because it is built in the least perturbed condition possible. It has to offset many effects, such as thermal and motion noise, Doppler effect, time dilation, etc. Besides, NIST scientists try to reach the lower temperature. With lower temperature, more cesium atoms can be trapped into a ball, and the bigger ball creates more entanglement, increasing the clock precision. But why do we need a super accurate clock? The more accurate clock offers more precise synchronization and a faster communication of network. This leads to more precise navigation, faster telecommunication, and internet. And it is very crucial for space traveling. To navigate in space, we have to measure the position, the velocity, and the course of the spacecraft related to Earth by time difference of signal sent and signal received. A millisecond errors can mean thousands miles error. Now, Einstein's hypothesis that time bends with gravity can be proved by placing one clock on the mountaintop and another one at sea level. With more precise clock, it is possible for satellites to monitor a tiny shift of gravity caused by Earth's sheet movement and strain, which leads to a prediction of earthquake.